Working with Inequalities Part 2. We will begin with an example. We're asked to indicate whether the value of x is a solution to the given inequality. If you recall, a solution means it will make the inequality true. We'll begin with a. The value of x is equal to 1, and we have the inequality 8 minus 4x is greater than 4. Our first step is to substitute 1 in for x. So this becomes 8 minus 4 times 1. Is that greater than 4? Following the order of operations, we have to multiply before we subtract. So 4 times 1 is 4. So this becomes 8 minus 4. Is that greater than 4? Next we subtract. 8 minus 4 is 4. So we have 4 is greater than 4. Is that a true statement? That is false. 4 is not greater than 4. So 1 is not a solution. For b, x is 5, so we substitute 5 in for x for both the left hand and the right hand side of this inequality. We have 4 times 5 minus 9 on the left and 2 times 5 plus 1 on the right. Multiply them before we add or subtract. We get 20 minus 9 and 10 plus 1. 20 minus 9 is 11, and if we take 10 plus 1 we get 11. So we have 11 is less than or equal to 11. Is that true or false? In this case it is true. 11 is not less than 11, but 11 does equal 11. So this is a true statement. 5 is a solution to this inequality. For c, x is negative 9, so we have negative 9 plus 8 in parentheses times 8. Is that less than negative 9? We have to do the grouping symbols, the parentheses first. So negative 9 plus 8 is a negative 1, and 8 times a negative 1 is a negative 8. Is negative 8 less than negative 9? Well, if we think of this on a number line, negative 8 is more to the right than negative 9. So this is false. Negative 8 is bigger than negative 9, not smaller. And part D, x is a negative 2/3. Substituting in negative 2/3 in for x, we have 6 times negative 2/3 plus 8. Is that greater than 9 times negative 2/3 plus 12? If you remember how to multiply fractions, 6 is the same thing as 6 over 1. So we're going to take the top number times the top number and the bottom number, which is 1, times 3. So 6 times negative 2 is negative 12 over 1 times 3 is 3. So this is negative 12 over 3. Negative 12 over 3 is a negative 4. On this side, again, 9 over 1 times negative 2/3 would be 9 times negative 2 over 1 times 3. 9 times negative 2 is negative 18 over 1 times 3 is 3. Negative 18 divided by 3 is a negative 6. So this becomes negative 4. This product becomes negative 6. So now we have negative 4 plus 8. Is that greater than negative 6 plus 12? Negative 4 plus 8 is a positive 4. Negative 6 plus 12 is a positive 6. So is 4 greater than 6? Again, on a number line, 6 is more to the right than 4. Therefore, it's the bigger number. This is false. Let's try another example. Here we have the histogram for the variable age. Age is a continuous variable, so these are not discrete, they're continuous values. We want to know what is the boundaries for the bin with the largest frequency. Well, the largest frequency would be this second bend, 90 students, and of course this is the midpoint, but this doesn't mean that there are 90 students who have an age of 18. We just know that there's 90 students who have an age between this lower limit and this upper limit, and 18 is the midpoint of that interval. So we need to figure out what are these values. What is the upper limit? What is the lower limit? So we need to figure out what is the class width. Here we have 18, here we have 24. That distance is 6. 24 minus 18 is 6. So how many bins are between these two values? Well, 18 is cutting this one in half, so we have a half here. Then we have a full bin, another full bin, and then the 24 is cutting this bin in half. So we have a half plus 1 plus 1 plus a half. That is 3. So there are 3 bins, 3 classes between 24 and 18. That distance is 6. So if we take 6, the distance, and divide it by the number of bins, which is 3, 6 divided by 3 is 2. So each bin has a width of 2. Let's see if that works. This is 18, then this would be 18 plus 2, which is 20. This would be 22, 24, yep, it works. 26, 28, and 30. So now that we have the class width, we know 18 is in the middle, it's the midpoint. So we have to take our class width and cut it in half. So if we take 2 and cut it in half, we get 1. So that means this number, this age for the lower limit is 17. This upper limit would be 19. And if I take 19 minus 17, I get a class width of 2. It works. So now we need to write this as an inequality. So if we have an age of 17, it would fall in this second bin. If we have an age of 18, it would fall in this bin. If we have an age of 18.5, it would fall in this bin. But if we get a 19, an age of 19, it would not fall in this second bin, it would fall in the third bin. So this bin is all ages from 17 all the way up to, but not including 19. We can get as close as we want to 19, but as soon as we get 19, we fall into this. So we have a compound inequality. We are starting from 17 and we're going all the way up, but not including 19. So that inequality can be written like this. 17 is less than or equal to x, the age, which is less than 19. So this is all numbers between 17 and 19. We can include 17, but we do not include 19. Next, it says give the boundaries for the bin with the smallest frequency. Well, this would be this last bin here. Looks like we have a frequency of maybe 2. So again, this has a class width of 2. So that means this lower limit would be 53. And this upper limit would be 55. Writing this as an inequality, we would say 53 is less than or equal to x, the age, which is less than 55. Let's do another example. On the last 3 statistics tests, a student scored 83, 89, and an 80. Let S represent the score that the student must earn. What is the value of S on the next exam so the student can have an average of at least 90? If you remember computing means, you add up the numbers and divide by how many you have. So that's our average, that's our mean. And this time we want the average to be at least 90. If you recall, at least means greater than or equal to. So our fourth test is the unknown variable. We're going to use S to represent that score. So let's write in inequality. So if we take the 4 values, add them up, and divide by 4, that's going to give us the mean, the average. We want this to be at least, which is greater than or equal to, 90. Now we need to solve this inequality. Our first step is to simplify. We can combine these and simplify this into one number. So if you take 83 plus 89 plus 90, you get 262. That plus S divided by 4, we want that to be at least 90, greater than or equal to 90. Again, solving, we want to get the S all by itself. We need to get rid of this number, the 262, and we need to get rid of the 4. Which one do we get rid of first? Since the 4 is dividing this whole group, this is sort of like grouping symbols, and if we follow the order of operation in reverse, the grouping symbols would be the last thing that we do. So that means we need to get rid of this 4. What is the 4 doing to the s? It's dividing. Therefore, we do the opposite. We multiply both sides by 4, and these 4 cancel. We are left with 262 plus s is greater than or equal to 360. Next, we subtract 262 from both sides, and we see that s is greater than or equal to 98. So the score for the last exam has to be 98 or more. According to the empirical rule, if a population has a bell-shaped distribution, and that's known as a normal distribution, approximately what percentage of values is within 1 standard deviation of the mean? Write this inequality and explain what this percentage means. Well, if we go 1 standard deviation below the mean, 1 above the mean, that is 68%. We could say 68% of the data will lie within 1 standard deviation of the mean. Well, that means the lower limit would be the mean minus 1 standard deviation. The upper limit would be the value of the mean plus 1 standard deviation. Writing this in symbols, we could write it this way. The mean minus sigma is the lower limit. The upper limit would be the mean plus sigma. Now I want to make a quick comment here. Would these be strict inequalities, or could this be less than or equal to and less than or equal to? Well, this is something that we're going to talk about when we get the probability. It turns out in statistics, in this case using the empirical rule, it could also be less than or equal to. So either one of these in statistics is essentially the same. And that's not true in all math courses, but in statistics, when we're dealing with area, when we're dealing with probability, these two are essentially the same thing. Okay, let's do one that has some values for the empirical rule. If the average age of retirement for the entire population in a country has a normal distribution with a mean of 64 years and a standard deviation of 3.5 years, what is the approximate age range in which 68% of the people retire? Write this as an inequality. Well, empirical rule can be applied here because we know it's a normal distribution. We know the mean. We know the value of the standard deviation. 68% would be 1 standard deviation below the mean, 1 above the mean. Using our answer from the last example, this compound inequality would tell us that 68% of the people who retire are in between these two numbers. Substituting these values in, we have 64 minus 3.5 for the lower limit, and then the upper limit would be 64 plus 3.5. Calculating these, we would say that the ages of 68% of the people who retired in this country is approximately between 60.5 years and 67.5 years old. Let's do our last example. What is the approximate age range in which 95% of the people retire from this country? So we're changing it from 68% to 95. So now we have to go 2 standard deviations below the mean and 2 standard deviations above the mean to catch 95%. That's what empirical rule tells us. Now substituting these values in, again, the mean is 64, standard deviation is 3.5. So now before we subtract, we have to multiply by 2. And before we add, we have to multiply by 2. So this becomes 64 minus 7 for the lower limit, and the upper limit is 64 plus 7, which gives us the ages of 57 to 71. So 95% of the ages of people who retire in this country is between 57 years and 71 years. Thanks for watching.